Let's continue our discussion next with this example where we considered this equation. We have already seen this equation many times. Let's again see it. The second derivative of y with respect to x plus y equals 0. So this is a second order linear equation and it's also homogeneous because of this 0 right hand side. And we have already seen that sin x and cos x are solutions of this equation on the entire real line. And we also know something about these functions, namely that they are linearly independent over R. And because of that linear independence, it follows from theorem 4.3 that any solution of this equation on R looks like this. If f is any solution, then f is a linear combination of sin x and cos x. That means c1 times sin x plus c2 times cos x, where c1 and c2 are some real numbers. You do understand how to interpret this, right? I mean, say some solution f is given to you of this equation, then there exist c1 and c2, some two real numbers, such that that function will be like this, will be equal to this for all x belonging to R. In general, let this f1, f2 up to fn be n linearly independent solutions of some nth order linear homogeneous equation. Then by theorem 4.2, this linear combination of these functions is also a solution of that equation, where these coefficients of course are real numbers. Also, by theorem 4.3, any solution is of this form, as we have just now seen with sin x and cos x. And because of this set of n functions which are solutions that are linearly independent is called a fundamental set of solutions. And this expression, this linear combination of those fundamental solutions where the coefficients are arbitrary real numbers or arbitrary constants is called the general solution of the original differential equation. And you can see the entire thing in the form of this formal definition. Let these n functions be n linearly independent solutions of this nth order linear homogeneous differential equation. For this to be nth order, this leading coefficient function a0 of x should not identically vanish where in some interval a comma b. If so, then this set is called a fundamental set of solutions of the differential equation on that interval a comma b. And this linear combination, general linear combination of these functions, where these ci's of course are coming from the set of real numbers and they are constants in the sense that they do not change with x. Such a function is called the general solution of this differential equation on that same interval a comma b. Those of us who already know about vector spaces would recognize the fact that the solutions of such an equation, which in general look like this, form a vector space of functions. The vector space of functions, where the domain of the functions is this interval and the codomain of course is the set of real numbers, and where each function is a solution of this, and that vector space has dimension n, and any such fundamental set of solutions is a basis. So that means if one goes back to the previous example where this is the differential equation, then this is a fundamental set of solutions. Note that the previous definition, that means this one does not say that there is only one fundamental set of solutions, because a vector space always has more than one basis. I mean, usually that's the case. There would be other sets like this also, but this is one of the sets. So this is the fundamental set of solutions and this is the general solution, where in this case on the entire set of real numbers. In this case, instead of a closed interval a comma b, we have the entire real line. What is the advantage here? The advantage here is that you only need to find two linearly independent solutions. That's enough, because they have the power to generate the other solutions as their linear combination. Let's see another example. Actually, this is also something we have seen already, just like this one. This third order linear homogeneous equation. The third derivative minus 2 times the second derivative minus the first derivative plus 2y equal to 0. We have already seen before that these three are solutions of this equation on the entire real line, and that too they are linearly independent. I can't remember if we have verified that these are linearly independent, but that's the fact, and that is why this is a fundamental set of solutions of this equation on the entire real line, just like that one, and this is the general solution again on the entire real line, where C1, C2 and C3 are arbitrary constants. But verifying that such functions are linearly independent on an interval can be somewhat difficult sometimes. So can we do something about that? Instead of having to go through the verification every time, is there some apparatus that will help us out in there? And the answer is yes, we have something. Let's see this next definition. Let f1, f2 up to fn be real functions on some closed interval. In this list, the functions need not be distinct. There may be repetitions also. Also, the interval need not always be closed. This is how the definition is given, but it can change. All of these functions have n minus 1th derivative on this closed interval. That means that every point of this interval, any such function is n minus 1 times differentiable. It may be differentiable more, but at least n minus 1th derivative exists at every point of this interval for all these functions. Then the following determinant is called the Wronskian of these functions. It's denoted by this symbol w, then within brackets the list of functions, and the determinant is this. The first row is just the functions in that same order. The second row is their derivatives in that same order. The third row would have the second derivatives, the fourth row would have the third derivatives, and the nth row will have the n minus 1th derivatives. Because we want these derivatives, that's why we assume like this. If n minus 1th derivative exists, then obviously the lower order derivatives also have to exist, because otherwise how can you reach this one? Okay, now what is this object? How will it help us deciding whether some given functions are linearly independent or not? This is how, in the form of theorem 4.4. Say you have any n solutions of an nth order linear homogeneous equation on some closed interval a comma b. Then they are linearly independent on that interval. I mean, these functions are linearly independent on that interval if and only if the Wronskian of these functions, which itself is also a function on that same interval, is non-zero at some point x coming from that interval. In other words, these functions are linearly independent on this interval if and only if the Wronskian is not identically 0 on this interval. And we have another fact about Wronskians also, namely that the Wronskian of some n functions is either identically 0 on some interval or never 0 on that interval. Exactly one of these two things is true. Now, if we go back to sin x and cos x on the entire real line and calculate their Wronskian, let's see what we get. So, the first row, it will be a 2 by 2 determinant. The first row has only the functions, and the second row has their derivatives in that same order. The derivative of sin x in R is cos x, and the derivative of cos x is minus sin x. So then you expand the determinant in your usual manner. Sin x times minus sin x is minus sin squared x, minus cos x times cos x is cos squared x, which is minus 1, and that is never 0. Do you see that? For all x in R, this thing which itself is actually a function of x, well, in this case it's constantly minus 1, but still it's a function of x, that is never 0. And that is why, by that theorem, this is a linearly independent set on R. And just like that, if you take these other functions, those 3 exponential functions, and calculate their Wronskian, e to the power x, e to the power minus x, and e to the power 2x, then of course you get this determinant. The first row has the functions, the second one has their derivatives. This one has the same derivative, I mean nothing changes. Here you have a minus because you have minus x as your exponent. Here this 2 comes down, and then once more when you differentiate, this one does not change. Here you get again another minus, so those 2 minuses cancel each other, and here you get 4. And then what you do, you recall some properties of determinants. From a determinant, from any row or column, you can take something common out if that's available. So we can take e to the power x common out from the first column, e to the power minus x common out from the second column. They together, they vanish. And also e to the power 2x from the third column, that remains. After you do all these things, the inside looks like this. So you can then expand this in your usual manner. You will see that this is minus 6. So the Wronskian as a function of x is minus 6 times e to the power 2x. Exponential function never becomes 0 if x is real. So that's how this is never 0. For all x in R, this is non-zero. So just like this one, the set consisting of these 3 functions is also linearly independent on R, on the entire set of real numbers. And the section itself ends here, and the video also ends. In the next video on differential equations, we are going to see some exercise problems, and then we will move on to the next section.